everybody. Here we go on our last page of 6.4 part 2. So we're going to look at this number 7 here. Let f be a differentiable function whose graph is shown to the right. The position of time t in seconds of a particle moving along a coordinate axis is the following. So here's the position function, and it's written as a definite integral. Okay, so once again, if the position function is written as a function with a definite integral, if you were to take the derivative of the position, you would, there would be inverses, and you would end up with just this f of x here. And so this graph of f of x here is going to be the same as s prime of t. Okay? So this is the velocity graph. Just imagine taking a derivative. Imagine a ddx coming in front here, knocking that out, and so that's the graph of f of x. And when you do the derivative, that t would pop in. Okay, so remember this function s of t represents accumulating area or net area or displacement. Okay, displacement. So where are you and what direction? Are you in the positive direction or the negative? Okay, so let's see. We've got this little chart here, and I'm going to actually do something. I'm going to keep this chart readily available. So I'm going to take this page off so I'm not constantly flipping. I know that's very distracting. So let's keep this kind of available and go to the other side of the notes. Okay. Okay, so I can just flip it instead of turning and folding. Okay, so use calculus notation in terms to justify each answer. If s of t represents the position, then what does f of t represent? Label on your graph. Okay, we just did that. And so that's going ahead and noting that the derivative was taken on that function, on this function here, and okay, so if we were to do s prime of t, we would put as d t here. Okay, and over here I said, when I was just pointing at a ddx right here, it would actually be a ddt. It's got to match. All these have to match. When I said ddx right here, I should have said ddt because all of those have to match. But we got it right over here. Okay, and so by that FTC number 1, that would all, and the t would just, you'd end up with this. Okay, so it's FT. So what does this graph f of t represent? And that would be, velocity. All right, so next piece. What is the particle's velocity at t equal to 3? All right, so at t equal to 3, make a nice point here for me. Very nice. So you could write v of t or f of 3 is equal to 4. Okay, and we're in meters per second, I believe. And that was a given point, which is nice. Okay, on what interval is s of t increasing? Okay, so remember that's the velocity graph, so we're looking for where the velocity graph is positive. So f of t positive, which means above the x-axis. Okay, so where are we above the x-axis? We are above the x-axis from 0 to 6. Okay, the next one, what is the position's position at time 6? Okay, so my position function is s of 6, 0 to 6, of f of x dx. So I want to get the area under the curve from 0 to 6 here. And luckily that's a nice little triangle. So 6 is the base, 2, 4, 6, 8 is the height. And we can easily do that. Okay, so now you can see we have a context of the problem. This isn't meters squared because this is a particle's position. So that's 24 meters. Okay, so it would be 24 meters to the right, but not meters squared because we're talking about a linear measurement. All right, at what time during the first 12 seconds does S of t have its largest maximum value? All right, so we're looking for f of t, the velocity, to be 0, and a maximum, the sign changes. Sign, not psi, sign changes. So I'm actually doing the explanation first here so I know what to look for when I flip. And the sign changes from positive to negative. So let's see where that is. Okay, and it's right here. So f of t is equal to 0 there, and confirmation that we go from positive to negative. Approximately, when is the acceleration 0? Okay, so it doesn't say to explain, but so basically we want to go from velocity acceleration, and so where will we have a 0 tangent line on velocity? So we're looking for an m tan. It doesn't have to explain, but we're looking for an m tan equal to 0 on velocity, and that's going to occur, right here. M tan of 0 on velocity. And that appears to be right at 9 seconds. Is the acceleration of the particle at time t equal to 3 positive or negative? So acceleration is going to be the slope of velocity, right? So we're going to look at the slope of velocity. Oh gosh, the graph's right here. Oh, it's right here. I keep flipping and it's right here. Okay, so here is this 3, 4. All right, and so we just want to know what this slope is. So basically we could just, this is linear, so here to here. So that's a 0, 2, 4, 6, 8. And here is 6, 0. So down 8. So A of 3 is going to be negative. All they really wanted to say, all they really wanted was that, but it's negative 8 over 6, which is negative 4 over 3. So negative as the slope here is negative. Okay, so slope of f of t at t equal to 3, a of 3 is negative 8 over 6, negative 4 over 3. So answer the question negative as the slope is negative, decreasing slope. All right, next question. Is position at 12 positive or negative? How do you know? What does this suggest in terms of the particle's position relative to the origin? Okay, so this is positive position. Positive displacement. Okay, so we're going one direction, and then this is negative position, negative displacement. So this is a bigger number. All right, so S of 12 is positive. There is more positive position. More positive area, more positive position or displacement. right? I mean, you could just basically say that the area under the curve from 0 to 6 of this f of x dx is greater than the area from 6 to 12 of f of x dx. And greater, you know, in terms of absolute value. Of course, it's greater, it's positive, but in terms of absolute value. All right, so I think that's it, except show graphically the total distance traveled. We're just going to pop this up. And total distance would be all this. Okay, next two little questions, kind of fun AP-ish, and then we're done with 6.4. If f of 1 equals 12 and f prime is continuous, and the integral from 1 to 4 of f prime of x dx is 17, what is the value of f of 4? All right, so read it through once, read it through again. All right, so we're going to start with f of 1 is equal to 12. F prime is continuous. We're going to start with the integral. This looks like a good place to start because I can integrate this derivative. It'll just be f of x from 1 to 4, and that's in question, okay? That's given and that's in question, so this looks like a good plan. I want to get that into the problem and that into the problem, so integrating the derivative will easily do that. Okay, then I also know that this integral is equal to 17. So we've got a little transitive property action here, that f of 4 minus f of 1 equals 17. F of 4 minus 12, that's given, 17. F of 4, a little pre-algebra here with calculus notation, 29. All right, and last question. Okay, let f of x equal to 2x minus 3. Find k such that 8 to k of f of t dt plus k is equal to integral of 2 to x f of t dt. So let's see here. Well, if f of x is this, then f of t is certainly. All right, so here we go. See that? I'm going to isolate k. So we can move that other guy over. Probably should have done that in the beginning. So k is going to equal this integral minus this integral. All right. So, and you could go through that and everything would work out really great. Let me get this confusing stuff out of the way on the bottom. Okay. You could go ahead and integrate both of those and then, you know, throw in your upper bound of x, throw in your lower bound of 2, minus upper bound of x, 8. Let all that algebra shake out. Sorry, I had a coughing attack. I took a COVID test. I'm negative. I just had a good old-fashioned cold. But you could be really smart and say, hey, those match. I got this match here. So what if I do this? What if I make this uncomfortable, and that will negate? Make that a positive, and then x to 8. All right, and then I can combine that integral and just go from 2 to 8. That'd be the easiest thing to do. Now, if that's too much, you could easily just do each one of these pieces. You could even do them here, and then isolate k. Just watch your math. So this is going to be t squared minus 3t from 2 to 8. 64 minus 24 minus 4 minus 6, 40 minus negative 2. K is equal to 42. Okay, so that's the end of 6.4, part 2. On to 6.5, the trapezoid rule. All right, see you guys in class. Bye.